Hello, this lecture will cover pages 209 through 215 of my lecture notes. Please print those pages out and have them in front of you as I present this lecture on Synchronous Logic Design, Part A, Designs 1 and 2. We're going to start out on page 209 and we're going to address a new phase of the course called sequential logic. In digital circuit theory, sequential logic is a type of logic circuit whose outputs depend not only on the present inputs, but also on a history of the inputs. This is in contrast to the combinational logic, which we spent the last 5 weeks on, whose outputs are functions of and only of the present inputs. In other words, sequential logic has storage, has some type of memory associated with it, while combinational logic does not. If you remember when we talked about combinational logic, once you set up the inputs, there was a certain propagation time through the gates and an output was produced. Well, with sequential logic, you still have that propagation time, but things happen at specific periods of time based on clock edges. And flip-flops add the memory or the history that we're going to need when we process the logic from one state to another state, and it'll become obvious as we go through this. Sequential logic is therefore used to construct some types of computer memory, logic control circuits, and finite state machines. Most practical digital logic circuits are a mixture of both combinational and sequential logic. The term synchronous logic is used to imply that the circuit outputs change states only on the transitions of clock. This is the foundation of sequential logic. On page number 210, we have a design procedure. If you remember, I gave you a design procedure for combinational logic. And if you follow that design procedure for combinational logic, it'll never fail you. And you'll be able to go from a specification to a final product just by looking at that combinational design procedure. Well, here is the synchronous logic design procedure. It has 9 steps. Now, I'm not going to read each one of these steps to you, but you should probably stop the video. You should probably read them very carefully. It's not going to make a lot of sense to you, but this is the procedure that I want you to go through in detail every time you design a synchronous logic or a state machine circuit for me. So you might want to keep this handy. On page 211, synchronous logic design. There are a total of 9 designs that you'll do for me over the next 2 weeks. Some of those designs we will do together, and some of them you have to do for homework. This is on page 444 through 445 in your textbook. But if you have the that's edition 12. If you're using a edition 11, which I think most of you might be this semester, it starts on page 409. So go ahead and if you need the author's paraphrase of my lecture, you might want to look at page 444 in your textbook or 409. Design number 2 and design number 8 out of the 9 designs, you'll be building them and testing them in the lab. And then I'm going to use that as a component for your grade in the 275 class. Here's the first design. The specification, my simple specification says, using the design procedure on the previous page, that's on page 211 or 210, design a synchronous counter using Jk flip-flops that will cycle binary 0, 1, 2, 3, 4, and then repeat 0, 1, 2, 3, 4, and so forth. Well, you could use the previous examples that I gave you, and you could decode this you could decode the fifth state. Notice this is a 1, 2, 3, 4, 5. It's a mod 5 counter. So you decode the fifth state and you make it the you make it the 0 state. But we're going to show you another way of designing synchronous counters, and this way is more advantageous because it provides the same result, but you don't have to provide the decode. In a lot of cases, it's a simpler circuit from a standpoint of construction and cost. So let's take a look at the first step. Here's our specification. The first step, if you look at page number 210, says determine the desired number of flip-flops needed in your design. This is based on either your maximum count or the number of states required in your state machine. Well, after giving it some thought here, we have to count up to 4. If you're going to count up here to 4 and you're going to do that with a binary counter, you need to have 3 bits. Think about that. You need to have 3 bits, a 1, 0, 0, to count up to 4. So you need 3 flip-flops. So n is equal to 3. That's your starting point on all these designs. You'll need 3 flip-flops. The next thing you do is you draw a state transition diagram showing all possible states, including those that are not part of the desired sequence. They're the don't cares. Include all input and output conditions. So we're taking a look here, and at this point there's no input conditions we have to deal with. We basically have our states, and our states are 0, 1, 2, 3, 4, and it goes back to 0 again. That's the procedure. Remember I told you on these state transition diagrams, each arrow represents an occurrence of a clock pulse, and each circle is a state. Very simple to go to these state transition diagrams. Well, they start out pretty easy, but it's not a difficult process. Once you get to the state transition diagram, it's all procedural from that point to finalize your design in all these problems. So this is a big step. This second step is real important. You're able to get to the state transition diagram. Again, this one's pretty easy, but I'm starting out nice and slow for you. The third thing you want to do is use that state transition diagram to construct present to next state table for all desired transactions. Include a row for every possible input condition. So here's the third step. Notice I have my present state over here. Here's my most significant bit, Q2. There's Q1, and the least significant bit, Q0. And here's my next state. Notice I'm just looking up here at the state transition diagram. Now, it's going to be beneficial for you to number in base 10 your states out here. You'll see that in the next example. So I'm numbering 0, 1, 2, 3, 4, each of these rows. Here's the present state, 0, 0, 0. You write it in. The next state, when the clock edge comes, you go to state 1, 0, 0, 1. You're in state 0, 0, 1. When you get a clock, what happens? You go to state 2, 0, 1, 0. You're in state 2, you get a clock, you go to state 3. You're in state 3, you get a clock, you go to state 4. And you're in state 4, you get a clock, you go back to state 0. This present state to next state table comes directly from your state transition diagram. We're sequentially, no pun intended, going through this. The third step. This is on page number 212. Or the fourth step, I'm sorry. Construct the Jk Excitation Table. And it's going to be the same for all these designs because we're going to use Jk flip-flops. If we used another flip-flop like an SR, you'd have to use an SR excitation table. But we're going to use the Jk Excitation Table, so you just basically have this available. Now, let's take a look to see how we come up with this excitation table. If you're in state 0 on a bit, and you want to stay in state 0, J has to be 0 on the input, and it doesn't make any difference what K is. I'll explain that in a second. If you're in state 0 and the bit goes to a 1, J has to be a 1, and it makes no difference. It's a don't care for the K input. If you have a 1 on a bit, on the output of a Jk flip-flop, and then on the clock you want it to go to 0, I don't care what J is, it's a don't care. K has to be 1 though. And if you have a 1 on the output of a Jk flip-flop and you get a clock and you want it to stay at a 1, Doesn't make any difference what J is. It can be a 0 and or a 1, but K has to be 0. Now, how do I come up with this excitation table? What I'm going to show you is you do this one time. Once you do this one time, you never have to do it again. So let's take a look at the truth table for a Jk flip-flop. There's the truth table for a Jk flip-flop, which you'd already have memorized by now. It makes this a lot easier. If we take a look and we have a 0 on the output of a Jk flip-flop and we want it to stay 0, J has to be 0. But K doesn't make any difference, because if K is a 0, if J is a 0 and K is a 0, it's a no change, so you're going to stay at 0. And if J is a 0 and K is a 1, that's a reset, and the output goes to 0, which is where you want it. Let's look at the second row. If you have a 1, if you have a 0 on the output of a Jk flip-flop, and when the clock comes you want it to go to a 1, J has to be 1, and I don't care what K is. Let's make J a 1. Let's make K a 0. That's going to set the output. Well, that's what we want. We want it to go to a 1. Or what if K is a 1 and it's a 1 and a 1? A 1 and a 1 gives us a toggle, and that 0 goes to a 1. So if you go through these this row 3 and row 4, you do this one time in your career. And then you just use this excitation table. The fifth step, use the excitation table to complete the state table and then construct individual K-maps for both the J and K inputs for each flip-flop. Like I said, this is all procedural. Let's take a look. We're going to construct the next state K-maps and final output maps for each flip-flop. First thing we're going to do is flip-flop Q2, the most significant bit. We go back and we look at the present state to next state table, and we draw, it's going to be a 3-variable map, because there's 3 inputs, 1, 2, 3. There's 3 inputs and 3 outputs. So it's going to be a 3-variable map here. So we draw our 3-variable map. Here's our Q2, here's our Q1, and here's our Q0. There's our Q2, there's our Q1, and there's our Q0, present state and next state. The only thing we do a little different here is we draw a diagonal line through each of these subcubes. I don't know if you could see that here, and we number these 0, 1, 2, 3, 4, 5, 6, and 7. And then we just go back here and we say we're at state 0. Your Q2 is 0 and it stays in 0. In state 1, Q2 0 stays in 0. In state 2, Q2 is a 0, stays in state 0. 0, 0, 0, 0, 0, and then we jump over here, 0, 0. What about state 3? When you're in state 3, Q0 is a 0, Q2 is a 0, and then the next state is a 1. We're just working with the most significant bit now. There's your 0, and there's your 1. What if you're in state 4? If you're in state 4, Q2 is a 1, and it goes to 0. There's the 1, and there's the 0. 5, 6, and 7 cannot happen. They're don't cares. So you put don't care, don't care, don't care, don't care, don't care, don't care on each of these. Now, all you do at this point is you use this next state K-map to produce your J's and your K's for the input for flip-flop Q2. We're still working on flip-flop Q2. So if you take a look at the excitation table, if you're in 0, move this down. If you're in 0, stay in 0, J is a 0, and K is an I don't care. I'm going to do both of these together. Same thing here. 0, 0. The J map is a 0. And when you do the K map down here, it's going to be an I don't care. And for 2, same thing. 0 and a 0. You go back to your excitation table. The Jk map up here is a 0, and the K map is an I don't care. Then you go to 3. You don't have to jump back. You can go right across here. Just remember you're going to the subcube 3. But let's just go to 3 last in this first row. You're in 0 and you go to 1. If you're in 0 and you go to 1, J is a 1. and K is a 0. Move that down, sorry about that. And K is a 0. Let's look at that one more time. For 3, you're at 0, 1. J is a 1 and K is an I don't care. There's your J is a 1. And there's your K. Your KK map is an I don't care. And then finally, state 4, you're at a 1, you go to a 0. Well, if you're at a 1 and you go to a 0, J is an I don't care. And K is a 0. Now, where would we at? That's the wrong one up here. Doggone it. If you're at a, let's do this again. If you're at a 1 and you go to a 0, 1 you go to a 0, J is an I don't care, and there's your I don't care for J, and K is a 1. I was looking at the wrong row up there, and you get a 1 down here. Then all you have to do is look at these maps and say, here's your Q2, here's your Q1, here's your Q0. And the largest, use your reduction techniques. Form the largest groups you can and use X's as wildcards. Well, this is what I get here as a group. I have to get that 1. I have to include all the 1s, and there's only one 1 there. And if you take a look at that, J2, the input J2 is Q1 and Q0. It's an AND gate, 2-input AND gate to form the J2 input of that most significant flip-flop. And down here, you know, I'm going to use all these X's, and I'm going to circle all this. We never had something like this before. When you circle everything, that tells you the K2 input is simply 1. It includes everything. It's VCC. You tied the K2 to a VCC. It's a logic level 1. I'm making one big group there. Now what you do here is you look on page 213, and on page 213, all you have to do is take your time, and you do the next state map for the Q1 flip-flop. Again, you get this next state map here from your present state to next state table. And then you use the excitation on each one of these. For the J and for the K, you can do them together. You take your time and you do this logically. You use the excitation table for the Jk flip-flop to produce these two maps for J and K. And you can see when you use your reduction technique, the input J1 is equal to Q0. And the input for K1 is also equal to Q0, the output of the least significant flip-flop. And then you do your next state map for your least significant bit. And there's what the next state map looks like. And if you do your final maps for J and K, this is your answers. I didn't do it here, but you end up with J0 input being a Q0 bar and K0 being a 1. And then finally you realize the circuit. And if you look at page 214, you can see on page 214, the last step, you realize the circuit for design number 1. And if you take a look at this, you put your flip-flops down. Here's your Q0, here's your Q1, and here's your Q2. Here's your out. This is your outputs right here. There's Q0, here's your output Q1, here's your output Q2. I'm drawing it like this so I have my least significant bit over here and my most significant bit here. And if you look, what was your J2 input? It's the AND of Q1 and Q0. You don't have to run this the whole way around to here, and you don't have to run this Q1 the whole way around to here. You can just label it Q1, Q0. I know that goes to J2. K2 was a 1. Now, really, how do you get a 1 there for K2? It's a pull-up resistor to VCC, but I'll let you put a 1 there. We know what that is. And here's your J1, which was Q0. You don't have to draw from here to here. Just write Q0 and Q0 for K1. And down here, for your least significant bit, if you looked at your final maps, J0 was Q2 bar. You don't have to run this output the whole way over to here. Just write it like this, and K0 was 1. And this circuit right here, if you build this circuit, and it's a pretty simple circuit, you will have a design that will count 0, 1, 2, 3, 4, 0, 1, 2, 3, 4, as long as you're getting clocks. Now, For design number 2, you will be testing your design in lab. This is homework here. So using the design procedure that we just went through, that's on page 210 of your lecture notes, design a synchronous counter using JK flip-flops that will cycle binary. Now this is our little different here. It's going to count not sequentially. It's going to count 0, 1, 2, 7, 5. 0, 1, 2, 7, 5. It's not a sequential counter. And you'll see the importance of that when we get to state machines. But at this point right here, this is the count you want. So if it's going to count up to 7, so you're going to have to think what that is in binary. You need 3 flip-flops. So that's your first step. Do your state transition diagram. These are pretty simple right now, but look, state 0, 1, 2, 7, 5. 0, 1, 2, 7, 5. That's important. Then you go from there to page 215. On page 215, you do your present state to next state table. Now remember I told you to list these base 10 numbers out here that you want your count sequence. This is where this will help you a lot. 0, 1, 2, 7, 5. If you write those in as rows here, you're at 0, you go to a binary 1. You're at a 1, you go to a binary 2. You're at a 2, you go to a binary 7. You're at a 7, you go to a binary 5. You're at a 5, you go to a binary 0. There's your excitation table. You do your next state maps for each flip-flop. I'm going to start with Q2. There's your next state map for Q2. Your final output map, I want you to do them and get a J and get a K. Then do your next state map for flip-flop Q1. Do your final output maps for your J and K for flip-flop 1, and then do your next state map for flip-flop Q0, your least significant bit, and find your final output maps and a Boolean expression for your J0 and your K0 terms. You can check your answers with multi-sim logic converter here. You'll need to complete this design this week for homework because we're going to do this in the lab. I want you to demonstrate this in the lab. You're going to hand this in, so do this very neatly on Quattro paper. Follow the design procedure. That concludes the lecture.